Hello students, this is Mr. Ezra. So over the past few videos, we have talked about a lot of things with logarithm and exponents, and I want to remind you that we have talked about some exponential and logarithmic equations already, and they were fairly simple to solve. Today's exponential and logarithmic equations are going to require some of the newer things that we've talked about. So there's properties for condensing and expanding, and we're going to learn something new called change of base that will help us to solve some of these exponential and logarithmic equations. So we are doing something new, but it's going to be tied with everything that we've done in this unit up until now. There are going to be many examples today, but before we jump into those examples, just want to remind you quickly about the properties of logarithms, these things that we've been practicing with expanding and condensing logarithms. They're not going to go away. Your job in some ways is going to be when you look at a problem is to decide, do I need to use one of those properties? And many times you will not, but sometimes you will. So you'll have to kind of look for where you can condense, and when you can, you'll do it. Before we look at some examples, and we're going to look at a lot of examples today, so buckle up, get ready. I want to show you something called the change of base formula. Essentially, when you have a logarithm that does not have a base 10 or a base that it's easy for you to calculate the logarithm, you can change the logarithm to be a division of the log base 10 of what's inside the log divided by the log base 10 of the base of your original log. So for example, if I had log base 5 of 16, my calculator may not give me the option to type in this type of logarithm with a base of 5. My calculator generally is going to allow me to do two types of logarithms. I can either do a log base 10, which is where we don't see any base written, or a natural log, which is ln. What change of base does is it says, well, you can change this base 5 to a base 10. You just are going to take the log of what's inside your logarithm divided by the log of the base of your logarithm. So in this case, that would be log of 16 divided by log of 5. And I've changed the base from base 5 to division with two base 10s. This actually would work if I change them both to natural log. So I could do natural log of 16 divided by natural log of 5, and it would still work. I mean, I really could change it to any base I wanted. I could do log base 2 of 16 divided by log base 2 of 5. I'm not going to do that, right? I'm just going to use a regular log base 10 because I can use it in my calculator easily. That allows me to put this in and get a decimal approximation, and we're going to be using that today. For example, if we have log base 3 of 7, I can get a decimal approximation of this by finding the log of 7 divided by the log of 3. The log of what's inside divided by the log of the base. Now, technically, this is going to be an approximation. I'm going to have to round it. It's probably not going to work out to be like a perfect whole number or integer or even a decimal that terminates. Instead, we're probably going to have to round it. But if we go out 4 places past the decimal, we've got a pretty precise answer, and we're going to know about what that log is equal to, and that is just fine. So you'll see that in later examples today, I'm going to use this change of base formula, and I want you to see it and be comfortable with it. Some steps for solving the types of equations we're going to look at first. If you can isolate the base, do that. If you have a logarithm, isolate the logarithm. If you have an exponent, isolate the exponent. Whatever it is that you're solving for, isolate it. If you can rewrite the left side and the right side to make the same base, like we were doing in the examples of equations that we looked at earlier in this unit, then do that. But if you can't do that, if you can't rewrite it to make the same base, then what we're going to do is we're going to rewrite any exponential equation into log form, and we're going to rewrite any logarithmic equation in exponential form. So by when we get stuck and we can't do anything else, we're going to change the form. And by changing the form, it should allow us to get to a solution. It is important with these types of equations that you check your answer. Logarithms especially sometimes give us extraneous solutions that algebraically we're going to get something, but when we plug it back in, we end up with like an error, or it just doesn't work out. We end up with an impossible thing that's not going to work. And we'll see some examples of that in a little bit. Example 1 today. All right, we've got 8 to the x equals 23. Well, my exponent is already isolated. And my variable's in the exponent, and I'm really stuck. I mean, I can't get a common base here. I know that 2 to the third power is 8, but I don't know a power of 2 that would get me to 23. So this is where we change the form. We're going to change it to a logarithm. And to do that, one way to do that is to say, well, the exponent is equal to log base 8 of 23, or log base 8 of 23 is equal to x. And now that I've got a logarithm with no variable, I can use that change of base that I mentioned earlier in order to get the approximate answer. And that is it. Pretty simple. So I get stuck in an exponent, I change it to log, see if I can solve the log. Second example, we have e to the x equals 72. Now this is exactly the same as the last one, except when you have an e, what kind of logarithm do you need to use that has a base of e? Well, it has to be a natural logarithm. So what we're going to do is, and this is maybe something that we haven't talked about before, so let's talk about it really quickly. If I have a log that has the same base as the base of an exponent inside my log, I can cancel them out. So since I'm taking the natural log of both sides of this equal sign, and this natural log has an understood base of e, since I have a base inside my logarithm and an exponent with a base of e inside the logarithm also, they are going to cancel each other out and leave us with just x. And by doing that, we now have natural log of 72 giving us our answer, which is about 4.277. Another example. This time the base is not isolated, right? Do not be the student who tries to multiply 3 times 2 here, because it does not work. This exponent is blocking multiplication. The order of operations says that you have to do exponents before you multiply. And I can't do this exponent because the exponent is a variable. Can't raise 2 to an x power. So I've got to find another way to get rid of the 3, to isolate. We want to isolate this guy right here. Well, how do I get rid of the 3? I divide both sides by 3. And by dividing both sides by 3, I get 2 to the x equals 14. Now I've isolated my base. I'm stuck. I change the form to a logarithm. I say that x, the exponent, x, is going to be equal to log base 2 of 14. So that's that swoop method. Log base 2 of 14 equals the exponent. Log base 2 of 14 equals exponent. I can't put log base 2 of 14 in my calculator, although some of you might have the ability. If you have a newer calculator and you want to ask me, I'll show you how to do it. It's pretty easy, but most of us are going to have calculators that do not do this for us. So we've got to use change of base by saying log of 14 divided by log of 2 to get our decimal approximation of 3.807. Next example, example 4. This looks like a lot. And what I guess I should say is, pause the video, write this guy down, and try it and see if you can get it once you start to get comfortable with these. But don't let the amount of work here fool you. It's really solving an equation and then doing this, adding this idea of changing form, right? I've got the 3 raised to the 2t minus 5 is my base and my exponent. I have to isolate that base, which means the 2 that is in front of the parentheses and the minus 4 that's after the parentheses, they got to go away. How do I get rid of them? Well, I'll start by adding 4 to both sides. And by adding 4 to both sides of the equal sign, the minus 4 is eliminated on the left. How do I get rid of the 2? Well, this is like saying 2 times everything in the parentheses. I can always undo multiplication by division. That's exactly what I've done here to get 15 over 2. Now I'm stuck. So I'm going to do that process that I mentioned earlier, where I'm going to take, I noticed that this exponent has a base of 3. So I'm going to take log base 3 on both sides of the equal sign. And that log base 3 is going to cancel out with the base of 3 leaving me with just 2t minus 5. On the right side, I've got log base 3 of 15 over 2. From here, I still haven't solved for t. T is not yet by itself. I have a little bit more work to do. So I have to add 5 to both sides of the equal sign. Now, in your calculator, when you start to put things like this in, your calculator is going to open a parentheses after you type in log, whenever you type in log. So you need to start using parentheses in your calculator. If it helps you to add them into your problem, you can add them into the problem too. But the plus 5 is not inside the logarithm, right? This is log base 3 of 15 over 2 first, and then we're adding 5. Then after that, we've got this 2t over here, and I still don't have t by itself, so what do? I divide the whole stinking thing, by 2. That gives me this log base 3 of 15 over 2 plus 5. Now, how am I going to put this in my calculator? I didn't show you that, right? How do I put it in my calculator? Well, I'm going to do log of 15 divided by 2 divided by log of the base, which is 3, plus 5. And then after I get that, I have to divide that whole thing by 2. So to put this all in my calculator at one time, I've got to use parentheses in several places. It might be a good idea to do the numerator first, that logarithm plus 5, and then hit enter and then divide by 2. Or just put parentheses around this whole part, which is saying divide that whole thing by 2. Either way. But that's kind of a challenge here, is making sure you're putting things in your calculator correctly. And I haven't been mentioning this, and I probably should every time. Plug your answer back in to the original equation. Use your calculator, 2 parentheses 3 raised to the 2 times 3.417 minus 5, close parentheses, minus 4. You might not get exactly 11 because you have rounded this answer, but you're going to get something really close to 11. And if you don't get something really close to 11, that is a clue that you have made a mistake along the way. That there's something that you did wrong. And when there's lots of work to be done, there's lots of opportunity for a mistake. Checking your answer ensures that the mistakes don't cause you to lose points, because you can always go back and look through the problem and make sure that everything that you did was proper and appropriate, and that you calculated things correctly. And all you have to do is check your answer, and you don't have to write anything down. You just do it in your calculator and see if it works. See if it gives you something that's close to the value that you started with at the beginning. Example 5. Again, the base and exponent that I want to isolate is e raised to the 0.5x. That means that the 3 has to be gotten rid of, and the plus 2 has to be gotten rid of. I have to isolate the every base and exponent. Everything else goes to the other side of the equal sign using an opposite operation. So I'm going to subtract 2 first to give me 3. I'm going to divide by 3 next to give me 1. Now that I have the base and exponent isolated, I'm going to write a log of both sides of the equal sign that has the same base as my base and my exponent. In this case, that's going to be a natural log that has the base of e. A natural log of e raised to a power, the natural log and the e cancel out, leaving just the power behind, 0.5x. Equals, and remember what we do to the left side, we have to also do to the right. So once we do this natural log on the left to get rid of e, we also have to do it on the right. So now our answer is going to be the natural log of 1 divided by 0.5. That's how we're going to get rid of the 0.5 that's next to the x here. So remember, you always have to solve for the variable. You eventually have to get the variable by itself. Our final answer is 0. If you plug 0 back in, it will give you a true statement. 3 times e raised to the 0.5 times 0 plus 2 is 5. Example 6. We're going to start with some logarithms for a few examples. Okay. The first question here, or the sixth example, but the first logarithm question, I have 2 times log base 5 of 3x equals 4. Well, how am I going to get rid of the 2? Remember that this is multiplication, and I can undo multiplication by division on both sides. 4 divided by 2 is 2. Now at this point, I'm stuck, aren't I? Remember how we got rid of those exponents with bases on we take the log with the same base on both sides? Well, when I have a log with a base of 5, I can cancel out by putting a base of that log's base on both sides. So I'm raising 5 to the log base 5 of 3x and 5 to the second power. And I do this because the log cancels out. It's not there anymore. I now have 3x equals 5 squared. That's 5 to the second power. 5 to the second power is 25. I divide both sides by 3, and I get 25 over 3 is my answer. I plug it back up into the original equation to check my answer, and I'm good to go. Example 7. When we talk about isolating the base, in this case we're talking about isolating the logarithm. And this logarithm has an understood base of 10. So this minus 5 that's not part of the log has to go, and I get rid of it by adding 5 on both sides of the equal sign. Once I've added 5 on both sides of the equal sign, I now have log of 5x equals 2. I know that my log has an understood base of 10, so I'm going to put a base of 10 on both sides of the equal sign and put whatever is already there as the exponent. So this is going to be 10 raised to the log base 10 of 5x power and 10 raised to the second power. I do this because the 10 to the log base 10 cancels out, leaving me with just 5x. Just 5x. And on the right side, I can raise 10 to the second power to get 100. My last step is I still have a 5 next to the x. I divide both sides of the equal sign by 5 to get x equals 20. Again, use your calculator, plug in 20, log of 5 times 20 minus 5. Make sure you get -3. If you don't, then go back and check your work or ask me to come look at it and we can figure out where you went wrong. Example 8. Isolate the log first. In this case, it's a natural log of x. So I've got to get rid of this 5 that's being added to that natural log. So I'm going to subtract 5 on both sides. That gives me with 2 times the natural log of x equals -1. I undo multiplication by dividing. I'm still isolating that natural log. That gives me -1/2 on the right side and natural log of x. So how am I going to get rid of the natural log? I'm going to put a base of e on both sides of the equal sign. It's going to cancel out the natural log and leave me with just x. And then I have it in my calculator to raise e to the -1/2 power. Now, I don't know if we've talked about how to do this, and it may be self-explanatory, but in your calculator, there is a button that is e raised to the, and you're going to hit that button, and it's going to say e raised to the, and that's when you're going to put in -1/2, and it'll give you this decimal. E is kind of like pi. You're always going to get a really long decimal. It's an irrational number. When you plug this rounded answer back in for x in your starting equation, because you're rounding it, you might not get exactly 4, but you'll get really close, and that is okay. We're almost finished. I know it seems like we've looked at a lot of examples today, and we really have, but I wanted you to see many different examples so that when you got to your practice, you had a good base to build off of. The next 2 examples are different than any that we've seen before. So I hope that you've been, if you've kind of gone, oh, well, I've seen this, wake up. This is new. This is different. Next few are different. What you notice about this guy is that the 2 logs that we have are on the same side of the equal sign. And that's a problem. I need to have one logarithm in order to change to an exponent or in order to do anything. So lucky for us, we have talked already in this unit about how to condense logarithms. That's why I reminded you not to forget about all of those properties for condensing logarithms. Addition of two logs becomes multiplication inside of one log. So we're going to condense this log of x plus log of x plus 3 to be log of x times x plus 3. Now that log has an understood base of 10. So in order to cancel out that log, I'm going to put a base of 10 on both sides of the equal sign. It's going to cancel out the log on the left, giving me just x times x plus 3. And 10 to the first power on the right is 10. Now we'll go ahead and distribute this x to get x squared plus 3x. Now, at this point, your brain should say, oh, quadratic. What happens when there is a quadratic? You have to factor it or use the quadratic formula or complete the square. You've got to solve it in a different way. We're going to try to factor this first. So instead of solving for x, we're going to get everything on one side of the equal sign by subtracting 10 over to the left, right? Get everything on one side of the equal sign to get the quadratic x squared plus 3x minus 10. And then we're going to factor it. And it factors to give you x plus 5 times x minus 2. Well, we set both of those equal to 0, right? We set x plus 5 equal to 0, and we get a solution of negative 5. We set x minus 2 equal to 0, and we get a solution of positive 2. All right, well, those are our two solutions, right? Wrong. When you substitute both of these back into the original equation, the negative 5 doesn't work. Now, why doesn't the negative 5 work? I mean, it should work. We just did all the algebra correctly. We factored correctly. Well, it has to do with the fact that when you plug this into the logarithm for that log of x over there, you get log of negative 5. When you try to put that in your calculator, you get an error message. And the reason is, remember that this log has an understood base of 10. And if I wanted to know the value of this, I'm really asking 10 to what power is equal to negative 5? Well, you can't raise 10 to any power and get a negative answer. There's just no way. It's not going to happen. It's impossible. It's not going to work. So because of this not working, we end up with an extraneous solution. It is important, especially with logs, to check your answers because sometimes you check them and you realize, wait a minute, that did not work. And when that happens, you have an extraneous solution and you do not count it as part of your final solution. When I plug in 2, log of 2 plus log of 2 plus 3 happens to be 1. It is true. It is my only solution here. So I'm hoping that this is the last example. It's possible that it's not. There might be one more for us to look at, but we're going to look at this one. So again, just like in example 9, I've got two logarithms on one side of the equal sign. I should at this point know how to condense those to become one logarithm. In this case, subtraction of two logs becomes division inside of one log, and that's exactly what I do, is I change this to be log of x over x plus 3. At this point, I'm stuck. I've got to get rid of this logarithm by changing form. The easy way to do that, I think, is to use a base of 10 on both sides of the equal sign, because 10 to the log base 10 cancels out, leaving me with just x over x plus 3, and 10 to the first power is 10. At this point, I'm going to multiply both sides of the equal sign times the denominator of x plus 3 so that I can get rid of that denominator. So now I have x is equal to whatever 10 times x plus 3 is. I distribute the 10 to get 10x plus 30. I'm getting closer to an answer. I've got to collect my variables to the left now by subtracting 10x on both sides, which gives me negative 9x on the left. I divide both sides by -9, and I get 30 divided by -9 is -3.333 about. That's rounding. So is that my solution? Well, when I try to plug in that -333 into this log of x, or even into this log of x plus 3, I end up with an error message in my calculator because I cannot take the logarithm of a negative number. It's not possible. So since this is an extraneous solution, and it was my only solution, I end up with no real solution, or no solution. Important to check these solutions to make sure that they work, isn't it? All right, this is it. This is the last one. I told you the last one might be the last one, but this is the last one. And this one's different than any other. And if you persevered and you're going to have this example in your notes, then you're going to be ready for the example like this, the few examples like this in your practice, on your test review, and on your test. If I put one of these on there, you're going to be ready for it. But if you didn't do if the student next to you didn't do their due diligence and they didn't watch this video all the way to the end, they're going to be missing this example unless you tell them about it, and they're going to have a tougher time. So I thank you for sticking with me for all of these examples today. I know there's a lot of them. This is our last one, though. This is the last exponential. And this one is very different. I want you to look and notice that we have e to the 2x minus 4 times e to the x minus 5. What's happening here is I have something that does not look like a quadratic that we're used to, but we are going to treat it exactly the same way that we would a quadratic. So if you pretended that this e to the x was an x, it would look like x squared minus 4 times x minus 5 equals 0. This is a quadratic that you can solve, that you can get behind and do. You would factor it to be x minus 5 times x plus 1. Well, it just so happens that instead of x minus 5 and x plus 1, we're going to use e to the x. Why does this work? Because e to the x times e to the x is e to the 2x, because x plus x is 2x. And the inside and outside of negative 5 e to the x plus 1 e to the x is negative 4 e to the x. And the last times the last gives us negative 5. So we're factoring, it just doesn't look like the type of factoring problems that we've seen before, and that's okay. Now, once you factor, you can use the zero product property, which says that you set the left factor equal to 0 and the right factor equal to 0 and solve them both. E to the x minus 5 equals 0. I first add 5 to both sides. And at this point, I'm stuck. So I'm going to put a natural log on both sides of the equal sign to cancel out the e and give me x equals whatever the natural log of 5 is. That happens to be about 1.609. And that is great. For the other factor, I set it equal to 0. I'm going to subtract 1. So I get e to the x power equals negative 1. And I think, oh, well, I've got to get rid of this e, so I'm going to take the natural log of both sides, and it's going to cancel out that base e and leave me with just x. So, essentially what I have now is x equals the natural log of negative 1. Put that in your calculator. What happens? Your calculator throws up some weird error message and says, I can't do this. It's not possible. Since it's not possible, that means that this factor does not yield a solution that you can use, and the only solution is going to be about 1.609. You can plug that into the x in the exponent and in the original equation and check it out. You'll get something really close to 0 if you don't get 0. Because we're rounding this, it may not be exactly 0. Well, that is it for today. That was a whirlwind of examples, but they're all important. And I know that when you see the length of this video, you grumbled to yourself. And if we were in class, we would be doing example after example, and you would be grumbling because there's so many examples. But I want you to see enough of them in your notes where you have lots of different examples to go back to when you get to your practice and you're not confused. But if you are confused and you need help, I'll be glad to help you out. Just ask me to come over.